Today, I'm going to talk about how to generate from the Strauss process using stitching. For those who don't know me, I'm Mark Huber. My research area is in perfect simulation and robust estimators. Now, by robust estimators, I mean estimators where you have some sort of certainty on the bounds. For instance, we could know the true value with some small probability of failure within some error limit. If the failure probability is given, that's our classic confidence interval. If both the failure probability and the size of the error bounds, for instance, we might want the upper bound to be within 10% of the lower bound, that's an approximation algorithm. Now, in order to create these robust estimators, there are generally speaking two ways of doing it. One is to find estimators that have a bound on the bias, and the other way is to work with unbiased estimators. Now, if you're going to work with unbiased estimators, you tend to need exact samples from difficult distributions. Now, by an exact sample, I mean drawing exactly from a hard-to-generate distribution. And the method that I typically use is called perfect simulation. Perfect simulation methods do generate exact samples from difficult distributions, and they utilize recursion in order to do so. There are many perfect simulation methodologies. The oldest is acceptance rejection. More newer methodologies include coupling from the past, partially recursive acceptance rejection, the randomness recycler, dominated coupling from the past, birth-death swap with bounding chains. Now, generally speaking, globally based algorithms like acceptance rejection take time exponential in the size of the problem. Locally based methods are typically polynomial time for nice parameters of the problem, but beyond those nice parameters, the running time becomes exponential in the size of the problem, much like acceptance rejection does. Now, the example that I'm going to talk about today is called the Strauss process. It's a simple repulsive point process. It's a process that has a density with respect to a basic Poisson point process. In a Poisson point process, you have a Poisson number of points that are proportional to the intensity parameter lambda and the size of the space. We draw that Poisson number of points and then uniformly spread them around the space. A Strauss point process has a density where we're going to introduce a penalty factor. For each pair of points within distance r of each other, the density gets a factor of gamma, which is some constant in 0, 1. Here's an illustration. In the Poisson point process with lambda equals 80 on the unit square, 0, 1 to 0, 1, on average we're going to have 80 points. The Strauss process, because it's repulsive, is going to have fewer points. Now here is a sample with gamma equal to 0. And in this case, you can see that it only has 20 points. Now the method I'm going to tell you about today can generate samples for lambda values on the square, which have never been done before. I've tried it up to lambda equals 200, for instance, and been able to get samples. So, how do we generate such samples from the Strauss process? The first methods proposed were Monte Carlo Markov chain methods that generate approximate samples, and those were birth, death, jump processes. You can also do this thing perfectly. The earliest method was, again, acceptance rejection, dominated CFTP, partial rejection sampling, and the new method I'm going to tell you about today, stitching. So stitching is somewhere in between the global and the local methods. And so it kind of has some of the behavior of both of them. Some spiritual ancestors of the method, partially recursive acceptance rejection. That also used a recursive scheme together with acceptance rejection, but it really belongs with the local methods. Divide and conquer had part of the stitching, but it didn't really have the stitching part. So that's what's new about that. But here is what stitching does. The first thing that we're going to do is we're going to split the state space. We're going to partition the space for point processes into two disjoint regions. Then we're going to use recursion on each of the regions in order to independently draw a sample. And then finally, we're going to try and combine those two samples on the different regions back into a sample that covers the whole space. That's the idea. Here's a small example. Suppose that we start with our unit square. First thing I'm going to do is I'm going to split it down the middle into two rectangles. on the left side and on the right side, I'm going to go ahead and draw recursively a Strauss process. And then I'm going to put those two halves back together to get a sample which I will accept if and only if there's no conflict along this boundary. Here's an example where I did the recursion, I generated the samples, but when I put them back together, it failed. And again, I'm doing gamma equals 0 for simplicity, but this method works for any value of gamma. So why does this work so well? Well, remember, Strauss processes have far fewer points than Poisson point processes. So that means that when I do the recursion, each half generated by the recursion has far fewer points than a direct Poisson point process. And that makes acceptance much more likely because I have fewer points that could be causing a problem. So generally speaking, if I'm looking at the running time for stitching, the time will grow with the size of the space. Unlike the local methods, it will also grow with lambda. But unlike the local methods, it is actually able to run in a reasonable length of time for values of lambda which are much greater than for the local methods. Now, in general, stitching works anytime I'm dealing with a factor density. And of course, classic examples of factor densities include the Ising model. In fact, any Markov random field by the Hammersley-Clifford theorem is going to have a factor density, and the Strauss process that we just saw. So for example, the Ising model, we're taking the product over factors that depend on the edges of a graph. If the two endpoints of the graph are labeled differently, we assign a penalty of e to the minus 2 beta. When the two endpoints are colored the same way, are labeled the same way, we assign a factor of 1. That's the Ising model. In the Strauss process that we just saw, for all of our pairs of points living inside our point space, we have a factor of gamma if the points are too close together. Otherwise, we have a factor of 1. Now, stitching works when you can break these factors into factors that only depend on one partition, factors that only depend on another partition, and factors that depend on the interaction between the two partitions. Those are the stitching factors. So what can we say about the correctness and the running time of this procedure? Well, the correctness basically follows from the fundamental theorem of perfect simulation. So that's not too much of a problem. But let's think about the running time. So suppose that I just ran acceptance rejection in order to get a sample from S1. I'm going to let P1 be the probability that a sample drawn from the reference measure is accepted as a sample from the density that we're looking for. Similarly, P2 is going to be the probability that acceptance rejection accepts on S2. And P3 then is going to be the probability that stitching accepts on S1 and S2. So given a sample from S1, given a sample from the density on S2, P3 is the probability that we accept them as a stitched together sample over the entire space. So the chance that basic AR with stitching accepts is going to be P1 times P2 times P3. Some of you may know that the probability that acceptance rejection accepts is 1 over the expected running time of the procedure. And so the running time of just basic acceptance rejection is going to be 1 times P1 times 1 over P2. The running time of basic acceptance rejection is going to be 1 over P1 times 1 over P2 times 1 over P3. Now, because our stitching procedure breaks the left half and the right half into recursive calls, now the amount of time that we have to wait to get the left half is 1 over P1. The amount of time that we have to wait to get the right half is 1 over P2, and the entire procedure is replicated on average 1 over P3 times. So when should you use stitching? When the thing inside the brackets is less than 1 over P1 times 1 over P2. Or in other words, you should keep using recursion until the probability of accepting on the left plus the probability of accepting on the right is greater than 1. Now, The result of this is for basic acceptance rejection, you're going to get a running time which is exponential in the size of your point space. For stitching, the runtime is going to be exponential in the size of the boundary between your space. As long as you're dealing with a relatively nice point space where the size, such as a rectangle or square, whereas you break it into pieces, you tend to get smaller versions of the same problem. But as I mentioned earlier, in practice, this can be much faster. So let's look at some numerical results. What did I find when I ran this algorithm? Well, this graph shows the running time for 3 different algorithms. In the red, we have just basic acceptance rejection. In the blue, we have the partial rejection sampling of Jerem and Guo. And in green, we have the acceptance rejection with stitching, what I'm labeled ARS. And what you find is that the AR is exponential. PRS is polynomial for a while, but then past a certain threshold for lambda becomes exponential again. Whereas acceptance rejection with stitching will be exponential in lambda, unfortunately, but the rate of the exponential is much less than for the other 2 algorithms. Here's a plot of the log of the times against lambda so that you can see what I mean. The slope of the acceptance rejection and the slope of partial rejection sampling once you're past the threshold are roughly the same, but the slope for acceptance rejection with stitching is much lower. And so that allows us to do values of lambda which are much greater than can be done with the local methods. That's all I wanted to tell you about today. Thanks for listening. You can, of course, email me at mark.huber@claremontmckenna.edu. My website is www.markhuberdatascience.org, and have a good day. Thank you.